The next four problems have the instructions solve the following log and exponential equations. So 14 and 15 are exponential equations because they have x's in the exponent, and 16 and 17 are log equations because they have logarithms in them. Now 14 is an exponential equation, but is different than 15 because number 14 has bases that can be manipulated. For example, this has a base of 4 on the left and a base of 64 on the right. I know it's 1 over 64, but we can manipulate that a little bit. Now, 4 and 64 can be rewritten as a common base. So, 64, I know, can be rewritten as 4 cubed because 4 times 4 times 4 is 64. And 4 is the same base on the other side, so I can really change how this looks so that they have the same base. So what we're going to do on number 14 is called change of base method. So 64 is equal to 4 cubed, but I don't need just 64, I need 1 over 64. So in order to get 1 over 64, I need to use a negative exponent. The negative in the exponent means flip it upside down or put it 1 over. So 4 to the negative 3 means 1 over 4 cubed. So therefore, I can rewrite this 1 over 64 as 4 to the negative 3. Because 4 times 4 times 4 is 64, and 4 to the negative is 1 over. So that will help us get the bases 4 the same on both sides. So now I have the 4 on the left and the 4 on the right the same. Once the bases are the same, then I know the exponents also have to be equal. So I'm going to set the exponents equal to each other. Some students like to think of it as canceling the 4's. Technically, I'm not canceling the 4's, okay? What I'm doing is if the bases are the same, then the exponents have to be the same. So I'm setting the exponents equal to each other. But I can see how some people might like to view it as canceling out the 4's. So then I can solve this simple equation and I get x equals negative 4. Now that is completely done. I do not have to check that. I can check it if I really want to, but I'm not required to check. I will be required to check on log equations, but not for exponential equations. Now on number 15, the base e and the other base is 11 and 18. I don't think they're going to have a common base like number 14, so we're going to have to use a different method. First of all, I can move the 11 over to the left side, or the right side, and that gets me e to the 4x minus 1 equals 18 minus 11, and that's 7, okay? Again, at this point, e and 7 are never going to have a common base. No matter what you do to it, they're not going to share a common base there. So I'm going to have to use a different method. And the other method that I'd like to do is I'd like to take the ln, the natural log of both sides. The natural log, taking the natural log of the left is really going to help me because the e and the ln are opposites of each other and they're going to undo each other. So the little invisible e there undoes each other, and I'm left with a normal size 4x minus 1 on the left. Now I need you to understand that ln 7 is some value. If I had a calculator, I could show you, I could plug it in and show you, but we don't need a calculator for this. But it is some value, okay? So when I try to solve for x and I add 1 to both sides, I cannot add 1 to the 7. ln 7 is a value, then after you get that value, you need to add 1 to it. So please don't write ln 8. It's not ln 8, it's whatever ln 7 is, then add 1 after that. And then the last step would be to divide both sides by 4. So my answer is x equals ln 7 plus 1 over 4. Please do not add the 7 and the 1 to get 8. Okay, that's just not going to work. Okay, again, you don't have to check that one. You're welcome 2 if you really want to. It's a little bit of a pain on this one to check it, but you could check it if you wanted to, but not required. Number 16 and 17, you are required to check, but only that your answer doesn't make the argument negative and therefore meaningless, really. So number 16 says log base 8 of x plus 4 equals 2. This is in log form. There's nothing being added outside the parentheses or multiplied in front of the parentheses. I don't have two logs adding, so it's already exactly in the log form that we wanted it. I can't figure out how to get x out of the argument, so if you can't get x out of the argument, I'm going to change it from one form to the other, from log form to exponential form. So the exponential form is going to be 8. The base 8 is a normal size 8. Raised to the 2, that changes signs and sides and becomes small in the exponent, equals x plus 4, that's normal size. And in one step, I've changed a log equation to an exponential equation, and now the x isn't stuck inside the log anymore. It's actually pretty easy to solve. So I have 64 equals x plus 4, subtract 4, and I get x equals 60. So this one was actually a very simple problem if you knew what to do first. Taking the first step from log to exponential, and the rest comes out really fairly simply. Okay. Now I did say that you have to check this. So when I check, I'm actually going to be plugging in 60 into the x. So I have log base 8 of 60 plus 4 is supposedly equal to 2. Now, I don't actually have to check everything. All I'm really checking is that 60 plus 4 is not negative. And it's not. It's 64. It's positive, and so I'm good. So therefore, this truly does work. If you want to take one more step, you could say log base 8 of 64 equals 2 and check that it does work. That's like a check for your insurance that you didn't make any mistakes. The check, if you're just checking to make sure the argument's not negative, is just checking to make sure that your answer is not extraneous. Okay, so number 17, I have two logs in this problem. So in order to make it look more like number 16, I need to take those two logs and combine them. Because the sign between the two logs is addition, I'm going to use the product rule, which says I can take the two arguments, x minus 6 and x plus 1, and multiply them. And when you take a moment to multiply x minus 6 times x plus 1, please don't forget to drag along the log base 2. I have seen a lot of students on the test just forget to write the log base 2 because they're like, oh, I'll get it in the next step. And then after that, then they just go ahead and solve without the log, and then the whole thing is wrong, and I can't give you very many points because you've made a mistake right in the beginning. Okay, so I have log base 2 of x squared minus 5x minus 6 equals 3. Now that I have it in the same form like number 16 was already in the beginning, I can change it from log form to the exponential form. And the exponential form is regular size 2, which is the base, raised to the 3 equals x squared minus 5x minus 6. 2 to the 3, that's 8. And now I can get one side equal to 0, which is 0 equals x squared minus 5x minus 14. And that factors into x minus 7 and x plus 2. So x is equal to 7 and x is equal to negative 2, potentially. I say potentially because we have to check our work. So when I check, let's see, I'll check 7 first. So when I plug it in, I have log base 2 of 7 minus 6. Is that positive? Yep. Plus log of 7 plus 1. Is that positive? Yep. And I'm not going to go any further. I'm just going to make sure that the arguments are positive. Now let's check x equals negative 2. So I have log base 2 of negative 2 minus 6. Uh-oh, right there. Now I know there's more to it, but it doesn't really matter. Negative 2 minus 6 is negative, and there is no such thing as a log of a negative, which goes back to the domain of the log functions that are only positive. So therefore, I have to take that answer out. So the only answer that I can have is x equals 7. I want you to write x equals 7 and x equals -2, then I want to see that you've put an x through -2 and only keep 7. Don't erase -2 entirely from your work. It was supposed to be there, but it just doesn't work. It's called an extraneous solution. So make sure that you put that in your answer, and make sure you take it out as an extraneous solution. For number 18, I have two parts, part A and part B. For the following matrices given in reduced row echelon form, give the solution for the corresponding systems of equations. I needed to test you on several different things on matrices, but matrices problems are so long, I couldn't have you do all of them fully out. So what I decided to do instead is, well, what if this was your last matrix in row reduced form? Can you get me the solution from there? So for part A, I'm going to take the reduced row echelon form and change it back into the equations. So here are the three equations, and when I get to the last one, I have 0 equals 0. Well, 0 equals 0 is a true statement, correct? Because this is a true statement, I know I'm going to have answers. I'm going to have a lot of answers. I just need to figure out which answers they are. So this would be a infinitely many solutions. Now, you can't just write infinitely many solutions. That's not good enough. That tells you how many they are, but they don't tell you what they are. So what we're going to do is we're going to let z equal some letter t. Okay, so I have one of my solutions in terms of some variable t, where I can plug in a number at a later date if I want to. Okay. Before I do too much solving, I prefer to take my equations and solve them for the variables. So I have x is equal to, if you move the 5y to the other side, that gets me negative 5y minus 3z, because I'm moving the z over as well, and that changes its sign. But the 11 stays positive because I didn't really move it. He just was staying on that side, so he stays the same sign. On the second equation, I'm moving the z, so that becomes negative z plus 3. And we've already decided that z is equal to t. Okay, now using these equations, I can say, well, I know z is t. So y is equal to negative z, but z is t, plus 3. So now I have that answer too, which is negative t plus 3. And I can do the first one as well. X is equal to negative 5y minus 3z plus 11. And who can I plug in for y? Negative t plus 3. And what can I plug in for z? Well, t. When I distribute here, that gets me positive 5t minus 15 minus 3t plus 11, which reduces to, what, 2t minus 4. So I have 2t minus 4. Excellent, and that's my solution. Now, if I wanted to, I could come in and plug t is equal to whatever number I wanted to and get as many solutions as I need. On our next problem, part B, I'm going to rewrite my matrix in equation form. So that gives me x plus 4y plus 2z equals negative 1. Y plus 2z equals negative 3. And then 0 equals 4. Okay, this is a problem right here. This is not true. So this is never going to be true. So I don't really even care what the other equations say. 0 never equals 4, and this is a no solution problem. There is never going to be any solution that makes 0 equal to 4, so you can just stop and write no solution on that one.